for the delay. So this is my talk today. It's an exercise that we're doing in our company. So our company, 2 years into existence, it's called Gaseous Electronics, true to the old name of the physical plasma, the general, more encompassing name. So it's an exercise where we're trying to build supposedly complex system, which is a multi-phase thermochemical reactor that has plasma in it. The old name of multi-phase reactions are heterogeneous reactions. That's one of the names. So let's try to explain each layer that we're building from a qualitative analysis point of view, which is something that's missing these days. So this is the content of the talk. You know, believe it or not, we're going to talk a little bit about the charge. Where is the charge? And then the plasma, which is matter energy action. Now this is just, like I said, this is how we are now think about engineering a solution that's we're going to be selling. What is the meaning of chaotic behavior in plasma has been known for the last 20 or 30 years. A few people exploited that. Again, a lot of grounded theories, phenomenological development over the last 100 years do already exist in the literature. They just need a little bit of effort to dig them out. Electrical probes, Langmuir probes, when switched to the so-called charge collecting mode, again, based on our definition of what is a charge in a plasma, like I said, they contain a lot of information, more information than the regular classical way of interpreting the readings of these probes. And then we will just show a comic of the everything together, you know, assembled, and we'll just comment on it. So let's get to it. So in the introduction, a qualitative analysis, this is something that there's a huge gap in the world about qualitative analysis. It has 5 pillars. Even narratives are considered qualitative analysis. But let's just talk about phenomenological and grounded theories. Greg Severn spoke about Langmuir work and within the phenomenological framework. And that was something that I really was glad that I heard about here in this conference. So that's a step in the right direction. Truly, we can tackle seemingly difficult engineering problems like constructing multi-phase thermochemical reactors by, again, taking layer by layer of complexity and assembles the layer first in our mind, and then we can do it in the laboratory. The commercialization of components in the last 5 or 10 years has been astounding, really. Things that we've never been thinking before are commercially available now, and that's a big driver and part of what's happening. So, charge. For the last 250 years, we've been told that the charge is that property of matter that allows it to experience a force, okay? Usually this is associated with any kind of field, usually. But plasma being the only type of matter where you can observe the two types, the two faces or facet of a charge, either carried on particles, as we can see them in traces, or as a continuum, such as in the space charge effect around the cathode in a thermionic discharge, for example. And these two are very important. So plasma, you can see the two. Now, people in the other 3 forms of matter, they care about matter and energy, okay? Switching from matter to energy, from energy to matter. In plasma, we care about matter and action, okay? Action in plasma could be collective behavior, but not necessarily. These days, collective behavior is not a condition of a plasma. If you're talking about gaseous electronics that exhibit a little bit of gaseous electronics, a little bit of physical plasma, collective behavior is not necessary. Sometimes it is something that you don't want, because collective behavior really, most of the time, you don't want it. Rather, you would settle for chaotic behavior, which is more natural. Any type of force, etching, sputtering, effects of magnetic, electric fields, instabilities, and 8 drivers you introduce for any thermochemical process, which we're going to be talking about probably. For one reason or another, Langmuir named a sheath region around the plasma, maybe because he thought about matter and action plasma, so he thought of a sheath. So let's just add another layer: order and chaos. So chaos is a natural occurrence versus order. So order and chaos are two things that are opposite. However, self-organization is not exactly order. It is a systems arrangement by external agents against which we find disorders. And then comes in a word that people, for a long time thought was ambiguous, which was entropy. And now we know entropy within the thermodynamics of things, what is entropy. But here comes irreversibility, okay? Then the uninitiated or the younger generations, they have much confusion here, okay? They think that it's just, in general, it's one-way direction. But we know that it's not. We will see that in a minute. Again, I'm stressing that point a lot here. This is a takeaway from this talk. Chaos in plasma is evident by the logistic curve. I will show that in the data. And then also in the nanoparticles that we're going to be introducing in this. If you want to introduce a nanoparticle in your multiphase reactor, that's fine. As long as it's below 1,000 nanometer, you're fine. You're good. Run-in motion, it's classified chaotic. You have both random walk and fractals working for you. The chaos theory itself has a mathematical toolbox. It's about time to bring it back. People 40 years ago, it was all the rave. Now, within the context of plasma, it's been unnoticed for the last 20 years. It's going to be solving a lot of problems, and it is actually. Turbulence, the overall design process, very robust toolbox. Now, let's talk about this thing again that I'm digging out. Theories and laws. So in chemistry, there are few laws actually. So, and then the issue, even these conceptions, again, irreversibility. If you want to apply the law of mass action, for example, this is a valuable thing. Now, when we set out to design a reactor, okay, with an engineering framework, we don't go and measure something and make it work for us. We design it to do this. So we can do stuff like that, okay, as long as it obeys the basic laws. Law of mass action is a valuable physiochemical law that wants to be revisited. Again, it gives free energy minimization. It gives both identical results. I wrote the word quasi here, but in reality, in the original publication reference, it was neutrality here. So again, for the people who are just an engineer who is starting out in this business, should just take a glance of what's happening. This is the concentration, this is the temperature. Then you go back and look at how these numbers worked out. Exactly identical, calculated from basic roots. And this is tendency to non-equilibrium. Okay, so again, I don't know if Greg's ever in here, but we were debating this issue here. And he spent a good few years worrying about expanding sheathes and pre-sheathes and whatnot. This curve was hand-drawn by the late Professor Noah Hershkowitz. And then it was just here. I mean, you have a planar with respect to the chamber, that's it. You get it. You have the saturation. By inspection, this is a paper that I published. This is the Verhulst Logistic, okay? You can see it's very clear. The behavior of the logistic you have a population of charged species or charged entities, okay? And they just behave chaotically at the logistic level, okay? And then you can do this easily here. You can go from the current, and then you can go from the rate of the change of the current without assuming anything about the Q, whether it's Q small or Q capital. This is the beauty of this thing, okay? Then you can go all the way here without assuming whether this Q is basically space charge or carried on the discrete particles. Okay, and this is some computational stuff. This is our design, initial design. You can do whatever you want. You can do the cusps. They're nice for confinement. You can do your bubbles here. People did this, the microwave bubbles generating them. This is a neat delta T, capital oval delta T, believe it or not, because it has the highest form of control and ignition and so on and so forth. I'll be happy to share this with you afterwards. This is to prove to you, in a reference, that now superconducting tapes are being sold by the meter in the markets. And you can imagine what you can do with them for commanding fields and such. Analysis, again, physiochemical laws, techniques and commercially available components are important. Chaos here is important. You have to lower your number of assumptions to proceed to your engineering exercise. Applications, like I said, controlled energy release processes. People worked for the MP's illumination heat production. Again, you can add layer and layer and layer. Once you know the basic principles, you're not violating the basic principles, you're taking advantage of the basic principles. And so on and so forth. So this is a summary. One more time, stressing this thing. People should go out and then look at the softwares that do these things. There are softwares that do qualitative analysis for you, give you insight before going and designing something to be sold in a time scale, in a reasonable time scale. Innovative, new, can be sold. That's what you get if you develop something under the umbrella of commercial R&D. And the rest is just what I said before. These are the references. I have more references in the abstract, okay, so you can look at them. And this is my email and phone number. We're based out of Riyadh, Saudi Arabia. I'll be happy to share with you any information about this talk and discuss it in any length or details you see fit. Thank you.